Okay, now that we're equipped to compare infinite sets, we're going to talk about the comparison between a couple famous infinite sets and see what we can say about their corresponding sizes. And I have to tell you, this is one of my favorite things in math. So the first thing we're going to do is talk about whether or not the natural numbers have the same size as the rational numbers. And so if they do have the same size, that would be the same as saying that we can find a way of listing all of the rational numbers in a one-dimensional list that only is infinite in one direction. So that might sound like a pretty difficult task. And it is, but there turns out to be a strategy that we could use in order to make sure that our list eventually hits every rational number. And so what I'll do is I'll start with just the number 0. And then after that, I'm going to write down all of the fractions that have 1 in the numerator and then an increasing number in the denominator. And then I'm going to start a new row now where I'm going to start by listing all the numbers which have a 2 in the numerator. And then I'll write out a couple more rows, although obviously at this point you can see what the pattern is. But I'm going to need maybe just one more row here. All right, and so now this is a two-dimensional grid that goes off to infinity every time you go to the right, and it also goes off to infinity every time you go to the left or down. And you can see here then that also every rational number that's positive, at least, should be hit by this grid somewhere. But some rational numbers are going to be hit more than once, and so that's already potentially an issue. But then the biggest issue for right now is that we said that if it has the same size as the naturals, we need to be able to write this as a one-dimensional infinite list. And so the way we can do that is by reading up diagonals. And so I'm going to read up this first diagonal here, and then I'll read up the second diagonal, and then I'll read up the third diagonal, and then the fourth one, and so on. All right, and so if I do that also, I'm going to, okay, so let me write this first. I'll read up the diagonals, and then I'm also going to have to skip repeats. And so if I write out the beginning of this list then, you could see that it would look like 0, and then 1 over 1, and then 2 over 1, and 1 over 2, and then 3 over 1, 2 over 2, which I skipped because that's a duplicate, and 1 over 3, and so on. And so I can say here that this 0 is sort of a case on its own, and then I can sort of break these up into the diagonals where I was reading them off. And there is a way of even characterizing these diagonals. I could say that the numerator plus the denominator for the first chunk right here sums to 2. And then it sums to 3. And then it sums to 4. And so that's really how I'm writing down this list. I'm just writing all the rationals where the numerator and the denominator sum to 2, then 3, then 4, then 5, then 6, and so on off to infinity. And so, except for the negatives, this list hits each q greater than or equal to 0 exactly once. And it's not a big deal to deal with the negatives because I could just insert the negatives in between all of the positives. And so if I insert those negatives between the positives, we have a list of q. And so that list of q implies that the size of the rationals is the same as the size of the naturals, at least in terms of cardinality. Okay, so at this point, you might rightfully be thinking that it looks like every infinite set has the same size as the natural numbers. But it turns out that the real numbers are way bigger than the rational numbers. in a very meaningful way that plays an impact in everyday life regularly. And the way that we can express that right here is by finally showing that there is no bijection between the natural numbers and the reals. In other words, the reals are just too big, and so there's no way of listing all the reals. And so the claim here, in other words, is that there is no list of the reals. And so our proof, you can imagine that it might be really difficult to try and show that there's no possible way of coming up with an organized list that eventually hits all the reals. And this sounds like an argument that would be tricky to prove directly, and for that reason, we're going to prove it by contradiction. And so that means that we'll assume that there is a list of all the reals. All right, and so if there is a list, what I'm going to do is just write down the first 4 or 5 numbers in this list. As a reminder, the real numbers can be expressed as infinite decimal expansions. And so my list might start with something like pi, for example, and then maybe I have something with a bunch of 9s and 1s, and then whatever. It doesn't matter what I'm writing down here. This is really just as an example. And so I'm just going to need maybe 5 numbers just so that I can see what I'm going to do to this list. And I can see that my mental pseudo-random number generator is not truly random, but that's okay. Okay, so now I need to show that there's some number that's not on this list. So we'll find a real not on this list. Okay, so I should write a little bit more in terms of the list that I just drew, which is that you can sort of see that every one of these columns here, if I line up the decimals perfectly, would have to go down to infinity as well. And that'll be an important aspect of this. And so in order to find a number that's not on my list, I'm going to start by circling the diagonal right here. And then I'm going to write down something that's related to this diagonal. So I'm going to trace the diagonal. And I'm going to write down a number 1 digit at a time. That disagrees with the next number on the diagonal. Okay, and so in this particular example, that would mean, for instance, that my first number can't be 3. And so I'm just going to choose anything. So maybe I'll choose 5. That's not equal to 3. It doesn't matter if I choose 6 or 7, whatever. I'm just going to choose that. And then for the next one, it can't be 9. And so maybe I'll choose 8. The third number on my list can't be 2. And so maybe I'll choose 3. And then I'm just going to keep on doing this. And so maybe I'll choose 3 for the next couple. And then I'll keep on going down that diagonal. And every number that I see on the diagonal, I'm just going to alter it to something different. It doesn't matter what it is, anything. And so the number that I end up with here, this 5.8333 and so on, off forever, this number is real. And also, importantly, it's not on my list. And so the reason that it's not on my list is it can't be any of the numbers on my list because one of the decimals in any number on the list was altered when I compare it to this one. And so in other words, if I go back to this list, it cannot be the first number. Let me try a different color here. Gray. And so it can't be the first number on this list because it disagrees in the first digit. It can't be the second number on this list because it disagrees in the second digit. It can't be the third number because it disagrees in the third digit, and so on, off forever. And so it can't be the 1,000,000th number because the 1,000,000th decimal place in this number, 5.833 whatever, disagrees with the 1,000,000th decimal place in the 1,000,000th number that I wrote. And so, in other words, that's because the nth digit of this number disagrees with the nth digit of the nth number on the list. All right, and so we could have done the same procedure for any possible list that claimed to have all of the reals on it. And so for that reason, we've shown that no list is complete. And so for that reason, the real numbers do not have the same cardinality as the natural numbers. So a couple historical notes. First of all, this proof right here is called Cantor's diagonalization argument. And when Cantor first proposed this diagonalization argument to show that the natural numbers and the reals did not have the same size, people didn't believe him. And they thought that the natural numbers and the reals and all infinite sets really had the same size. And so this caused quite a stir, and it took a while before the mathematical community accepted this as true and realized that there were sets of varying infinite sizes. And the other thing is that this does, like I mentioned before, play a sort of practical role in reality. And the way that I could describe that is if, for example, we wanted to talk about the temperature in the room where you are right now, and we wanted to talk about the probability that that temperature is a rational number. And so we already saw that the real numbers are much bigger than the naturals, but the rational numbers are the same size as the natural numbers. And it turns out that the real numbers are so much bigger than the rational numbers that the probability that the temperature is rational at any exact moment is exactly equal to 0. There's no way that the temperature right now in the room where you are is a rational number because there are so many more irrational numbers. And so that does play a role in a lot of modeling and sort of just any context where we care about how likely something is to happen.